It's even a Monday. Okay, so last time we looked at solo objects and their center of mass. I did the meter stick demo for something that's symmetrical. I showed you a video of when it's not symmetrical and how would you find it experimentally. Overall though, most of the problems you'll see now on are going to be those collisions, whether they come together or separate, whether they stick together or not. We'll look at collisions and you see the individual objects, but you have to imagine it as a system. Where's the system center of mass? And if you haven't learned, I'm visual, so I typically say, well, X marks the spot, right? I put a symbol there to show myself, okay, this is where it is. And where we left off last time, your center of mass of the system can be moving as well. So what determines if it's moving? Well, are the objects moving, right? This is page 11. It's PowerPoint slides. And so we did the center of mass position. That one was nice because it was equal mass, so it's dead center. And then notice we modified the mx plus mx plus mx to mv plus mv. Hey, that's like momentum plus momentum, right? And so this system momentum before the collision is how we found this velocity of your center of mass for the system. Everyone good on that little recap? And then part two, we did kinematics with your imaginary center of mass location, right? And so if there's no external forces on the system, then the system doesn't accelerate and your system has a constant velocity. And so we needed to do the constant velocity to get the displacement so we could find out that after 3 seconds, where is that X marks the spot? Good. So that's how, where after 3 seconds, that's where our center of mass would end. So maybe our final of center of mass is at about 23 meters. And the initial one was at 14. Now, we don't know if the collision has occurred or not. 3, at that same 3 seconds, so 3 seconds have passed. If your first object is at the 15 meter mark, where is your second object? And so, using our system center of mass that we now know its final position, we can use, and I'm just putting some F's on it, the final position of the center of mass for your system equals M1, V1, and technically, oh, I'm sorry, X1. And these are final, gosh, X1 final. There we go. And then for the second one, X2 final. And I'm just adding the F's because originally it was technically the initial positions all over our system mass. And so now we know where your system's final position is. We solve for that up above, and we got what, 23? Is that what we had? So we know it equals 23. 5 is the first mass. They tell us it's going to end at the 15 meter mark. Oh yeah, you'll need calculators. Second mass is also 5. And this is the final position that we're looking for object 2. Divided by the system mass. You can reduce it or just multiply both sides by 10. So we would get what? 230 equals 75 plus 5 times what we're looking for. So 230 minus 75 divided by 5. Let me know what you get. 31. Sounds familiar. But it started at 28. It was moving to the left. But after 3 seconds have gone by, it's at position 31. What's happened somewhere between 0 and 3 seconds? It changed direction because what happened? The collision, right? So we could break it down and do all this again at 2 seconds, at 1 second, right? Maybe we even solve for time at which they have the same position where the collision occurs. That's another problem for another, another day. Good on this? Okay, the next one we're going to do is an explosion midair. It's the one just below. We're going to go to that one. It says the object explodes at some point between t=0 and t=2 seconds. So we don't know if it's at 1, 1.5, or something weird like 1.82, right? We don't know exactly when it explodes. When it explodes, it breaks into 2 equal pieces. Thank you very much. At time equals 2 seconds, one piece is found at 3 meters in the horizontal and 8 meters in the vertical. So this is going to get into that 2-dimension a little bit. Don't worry, we're not going to have to worry about angles. Where is the other piece located? And so here we are, picture 1. You start at 0, 0 mark, if you will. It's going to go straight up, 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 up. Now, technically, isn't it in free fall? The explosion is internal to the system. Are there any external forces on the system? Gravity is our external force, right? It's a projectile. And so just note to self, the external force on the system is the gravitational force. Now, they didn't give us the mass, but we know it maybe starts as 2m, and then it's going to break up into m, and then another m is what we're trying to solve for. Determine the center of mass at 2 seconds. And so again, gravity's acting on it from the beginning. After the explosion, it's still gravity acting on the system, right? And so this net external force is going to be for the whole entire time. So we can just do projectile or kinematics since it's 1D for the system. Good. Now I think we do need one little edit. And I think my memory is correct. We need an initial velocity, okay? Because if you remember in kinematics, you got to have an initial velocity for every equation. And so I think if I remember correctly, it's 25 meters per second. I'm giving it to you. It got deleted. So we had teacher copies of all these with all the answers, and we had to delete, and we deleted a little too much. And so this is going to be given. I'm giving it to you. 25 meters per second. And so now we can do that kinematics for the system. And so we know initial velocity, initial positions, we know time, and we're looking for where the center of mass, that final position is. And I'm putting YF because it's going straight up, 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 up. And so which equation? Good old kinematics, which one do we use? It's the second one, because do we know the final velocity? No. And so I'm going to write my Y's. Little review time, right? And so vertically, it starts at 0 position. It's solved for final vertical position. Initial velocity is 25. The time is 2 plus 1/2. What's the acceleration on the system? Negative 9.8 or negative 10. Why negative? Ms. Earhart, with energy, you were just using 10. Remember, it's moving up, but gravity's acting down. Kinematics is a vector. Okay. And then 2 seconds again, don't forget to square that one, not both, just square that one. And so we end up with 50. And then 2 squared is 4 times 10, negative, right? Negative 40, and half that, negative 20. And so the final position vertically of your system center of mass is a positive 30 meters per second. Now, does that mean each of the objects is also at 30? No, this is what the system would have done had it not exploded. But it does explode somewhere in between the 2 seconds. So one of the parts is actually ending at 8 meters. And there's a horizontal offset. Now, we didn't do anything horizontally with it, because horizontally, what would be your system center of mass location? 0, because gravity is a vertical force. It's not going to change the horizontal motion for the system. And so it's going to remain at 0. Now, each part doesn't, but your system does. Do you see the separation between the individual objects and the system? Okay. Use your center mass formulas to determine the position, and we're looking for X and Y here, for the second piece. And again, it's equal mass, so that's nice. And so one of these, we really don't need to do the equation. Initially, you have 0 meters in the horizontal for your system, right? In the end, it's going to be 0. Well, one piece goes to the right, 3 meters. Gravity doesn't affect horizontal, so where's the horizontal position of, and I'll use the 2 label since in the picture they show 1. So X2 final would be what? Negative 3. And it's that way because they're equal masses. Remember to be careful if they were, a 2-to-1 ratio, a 3-to-1 ratio, you got to do the ratios with the distance. And I'd probably use the formula or slow down on that one. Vertically, now you may be able to do the vertical, but we'll use the equation to get a little bit more practice with it. So our system center of mass final vertical position equals M1Y1 final plus M2Y2 final all over system mass. Well, we just found the final for the system should be 30, bless you, equals, I don't know the mass, but I went with 2M and then MM, so I'm going to use M. Y1 final is 8, that's given up above, plus another single M, and we're looking for that Y2F. All over, what's our system mass? 2M. So notice the variable M is going to cross out, cancel out, but the factors are still there. And so 30 times 2 is 60, minus 8, 52. So Y2 final, it's going to be at a positive 52 meters. Good deal. So one explodes right and down, the other one explodes up and left. Hopefully that makes sense. Why, right? Okay. We got one more big problem here. I've got a simulation to go with it, okay? And so the grid line that you see top right, I'm going to pull up a PowerPoint and show you the simulation that goes with it. And it actually, I think the numbers agree with the problem we're going to do down here. And so PowerPoint, let me new share. Okay, and I want to present. Is that button? Yes. Okay. And so here it says, determine the location of the center of mass for each second shown. And so I'm gonna do clicking, and I think you see a little bit of what's coming, but imagine you saw a blank. And so when the timer begins, where is your system center of mass? Now be careful. This is not equal masses. It's a 2-to-1 ratio. Notice the grid lines for the distance. So X marks the spot where? At 1/3 the distance, because you have 2/3 the mass. And so if the left side is 0 meters and the right dot, the blue-green dot, is at 3 away, so it's at the 6-meter mark, what position is your system center of mass? How many meters? 2. And so on yours, do X marks the spot. Now, initially, one of your objects is not moving, but the other is. Can we go ahead and calculate what the velocity of your center of mass is doing? And they don't tell us to do this, but just to show, let me see if I can write. VCM for your system equals that M1V1 plus M2V2. And these are all initial, just to be clear, divided by your system mass. And notice one of your objects is not moving, and if however you want to go in order, how about 1 kilogram is M1? So that's going to zero out. And so VCM of your system is going to be 2 times a positive 3, just to remind you and everybody that this is a vector, right? Divided by your system mass of 3. No calculator needed. How fast is our red X going? 2. So that means, again, assuming there's no external forces, the problem didn't mention one, and so not even gravity. And so if there's no net external force on the system is going to keep doing what it's doing. Newton's first law, right? And so it would be a positive 2 meters per second before the collision and after the collision. And you're like, but there's a force during the collision. It's internal. It's between your two objects, right? It's not an external force on the system. Okay. And so in the next second, where's everybody going to be? Well, red dot is going to move 3 meters in 1 second, right? Green's just going to keep staying at rest. The collision hasn't happened yet. Where's the red X? Right, you can either do the 2-to-1 ratio again, or you can recalculate, or now we know it's moving 2 meters every second. And so it's at that 4-meter mark. So you might want to add the red X's to your picture. I don't think those are there, right? Okay. In another second, what happens? Our red moves another 3 meters, but wait, where did it go? What happens at our 2 seconds? This is where the center of mass for red ball overlaps with the center of mass for the green ball. And when the 2 individual center of masses overlap, what can we deduce? That's where the collision happens. And so at 2 seconds is our collision. And if your 2 individual objects overlap, where's your system center of mass? Same spot, red X. Now what happens after the collision? So this is where it may be unclear unless you have a nice animation or given information. We don't know if these 2 stick together or not. We don't know if it's elastic or inelastic, right? And so I'm going to keep with the simulation. Again, the problem below aligns with it. They're not going to stick together. But notice red does not move another 3 meters. It moved half a box. It moved 1 meter in the next second. So it kept moving to the right, but now we can see it has slowed down. And so now the final velocity of red after the collision is 1 meter per second. Green ball has motion now. It's no longer at rest. How fast is it moving after the collision? 4. It moved 2 grid lines in that 1 second interval. And so now it's 4 meters per second. What about our red X? Does the collision change the system center of mass velocity? Is it an internal or external force? It's internal. So the only thing to change the system would be an external force. And since none were mentioned, then the acceleration of the system is 0. What's the velocity of the center of mass after the collision? Still 2. So I can go up here and just say initial. And so that collision, yes, there's forces, but it's internal to the system. And you can look, do your 2-to-1 ratio. You should still see it match up. Red X is now at the 8 meter mark, right? And if we kept it going, now no more collisions, they would just keep doing what they're doing, right? Red's going slower, it's not going to catch up to green, right? Everybody good on this simulation type? Okay, and I can post the PowerPoint so you can take a look at it if you want. But we're going to do the math. I guess I don't want to keep those. Head back to OneNote. Okay, so the only thing really, hopefully you drew some calculations, but the red X, your system center of mass, is going to keep doing what it's doing. 1 grid line each second, 2 meters per second. Yes? Okay. And so down below, they give us the before and after. What would the collision look like if we changed frame of reference? Now, what I'm about to show you, I don't want to spend a whole lot of time with. I don't think it would be required. It's one of those tricks, simplifications, okay? Notice how everything's given to you from the simulation, right? What do you solve for? Well, pretend they didn't give you the velocities, final velocities, okay? Maybe it's like that one we did previous where, okay, it's an elastic collision. By the way, that's one of the requirements for what I'm about to show you. And so it's got to be elastic. It doesn't have to be equal mass, but there's 2 unknowns. And if you were here, let me pull it up. Where was it? Page 6. Yeah. Y'all remember all this long algebra, 2 unknowns, 2 equations, conservation of momentum, conservation of kinetic energy when it's elastic. And we had to FOIL and quadratic and all that stuff. Remember that algebra mess? So that's when it's 2 unknowns with an elastic collision. Well, an alternate to all that is going to be what I show you here. And so pretend you don't know the 2 final velocities. We know what it should be. Pretend we don't know. How can we, without doing that double solve for both final velocities? What would the collision look like from the frame of reference of the center of mass of the system? Let's do a little Einstein thinking. He always said, what if I could ride a particle of light? What if we rode the red X? What would we see before, during, and after the collision? What if we rode the red X, is what I like to say. What if we took this from the point of view of the center of mass reference frame? And so I'm going to be toggling back and forth between the simulation so we can see the red X, okay? So if I'm writing the center of mass red X, what's this initial velocity? By the way, our example switched from dots to a shopping cart and bowling ball. Sorry about that. Okay, and so let's switch it. So your red information is the shopping cart. Your green information from the simulation is the bowling ball. And so once again, we've got 2 kilograms and 1 kilogram. And initial velocity from the original, it's a lot of subscript writing, was, what was it, 3, 4? Oh, I've already forgot. 3 meters per second. The initial velocity of our second object, maybe I switched to green, in the original reference frame is 0. And we know the mass of both. That doesn't change. And so here's what we're going to do, slightly different. We're looking for these final velocities. I got 2 unknowns. I got to have 2 equations. You do have to recognize that this is only going to work for an elastic collision. Okay? Only work for an elastic when you have 2 unknowns. And so it's kind of a 4-step process. You don't have to do the quadratic necessarily. Okay? It's about switching reference frames. And so let's see if I can get this right. Where's some space? And so step 1 is to get your initial velocities in the center of mass reference frame. Gosh. Is to get the initial velocities in the center of mass reference frame. So RF is going to be reference frame. And so if I'm writing the red X, I'm going to, and think about cars driving on the highway. You may or may not drive, but hopefully you can relate. We're doing relative velocity here. So if I'm writing the red X at 2 meters per second, and somebody's coming up from behind, if we think about this simulation again, so if I'm the red X and I am moving 2 meters per second, but somebody comes up from behind at 3 meters per second, how fast do I say they're going? 1 meter per second, right? And they're coming towards me, okay? How fast is the green stationary object in front of me if I'm going towards it at 2 meters per second? 2 meters per second, but I'm going towards it now, okay? And so I would say, well, it looks like the red dot or the shopping cart is going to the right at 1 meter per second. If I'm writing the red X, yes? But I would say, oh, the green, it looks like it's coming towards me at 2 meters per second. If I'm writing the red X, yes? So in order to get that, step 1, we're going to take our initial velocities in the original reference frame and subtract the system's center of mass. And so for each object, so for V initial 1 in the center of mass reference frame, it would be 3 meters per second minus 2 meters per second. And in the new reference frame, that would just say, well, it looks like it's going to the right at 1 meter per second. For the green, V initial 2 in the center of mass reference frame would be 0 minus 2. It would be a negative 2. Looks like it's coming towards me at 2 meters per second. Yes? Okay. And then, trying to use my colors. If I mess up the colors, you'll just correct me. Then step 2, is this the part where we're, I think this is the part where we're, the elastic collision occurs. Oops, occurs. And if you think back to that one example we did, now it had equal mass, but elastic just traded velocities. Well, here, switching from the center of mass reference frame, we get to do the same trick, okay? They just switch velocities, okay? And so my red, this is the final velocity after the collision for object 1, but we're still in the center of mass reference frame. So it would be a -2. And the final velocity for our second object in the center of mass reference frame would be a +1. No, something's not right. That's only going to get us 3 steps. Hold on. It's just switch signs. So a little edit here. They switch signs. And so the red would not be a +1, it would be a -1. And the green would not be a -2, it'd be a +2. I think this is going to work. And then step 3 would be to get back into the original reference frame. So to get back into the original reference frame, we got to add back in the system center of mass, the center of mass velocity. And so it would be the final in the center of mass reference frame plus VCM. So for red, it would be now in the original reference frame. It'd be that -1 that we just had plus the 2. That's VCM. And here we get a +1. And then for the green, final velocity to get back into the original reference frame, it would be that +2 that we just had plus VCM. And that comes out +4. And hopefully those numbers are familiar because from the simulation, isn't that what we had? And if we go back to the other page where the velocities were given, oh wait, I think this has the misprint as well. Because from the simulation, we know it was moving green 2 grid lines each second. So this didn't get changed as well. So that one should come out 4 meters per second. 1 is correct. Okay. So if that was like, whoa, what's this writing of the red X? What's up with this? Your alternate, just FYI, switching colors, the alternate for an elastic collision is to just do that conservation of momentum for your system in the normal type of reference frame and conservation of kinetic energy. Since it's elastic, it's only a challenge when you have 2 unknowns. Okay, so if you'd rather just stick to the 2 conservation statements and put them together, solve for 1, put them together, possibly doing a FOIL and or the quadratic, that's fine. Or you can ride the red X and do this little trick, okay? Chances of you having to mathematically do both of these on the AP exam are pretty slim. But, you know, for those that appreciate the math, hey, it works out either way, okay? And so when it starts talking any problem about reference frame, right? If you're in the car and someone's in the car with you and you look at each other and you high five each other, if you're both going 40 miles an hour, then what's your velocity relative to your friend? 0, right? So reference frame is a big idea in physics that you need to be ready for. Maybe one question is about reference frame, okay? But this is using reference frame to get those unknowns. Good deal? Okay. Let's do a AP level center of mass free response type. So we're going to skip a few pages. What's next? 13. Okay, so these are, oh, let me show you the no, I already showed you that simulation. So that website is the balancing carts, the red and blue one that I showed you last time. And so we already actually answered those questions. What's here? Maybe that's our bell ringer next class. Let's go to page 20 now. So this is an AP level free response that does use center of mass. Page 20. And so we've got a 1 kilogram ball sitting inside of a 2 kilogram wagon. Oh, yay, a 1-to-2 ratio. That's nice. Initially, ball and wagon are both at rest. And so your VCM would be what if both parts of your system are at rest? 0, right? No equation needed. So if both objects are 0, your system is 0. Similar to the boy surfboard and or what was it, ball, canoe, and Mr. P video. You remember that one where he threw the ball in a canoe? Started at rest. Okay. Then a constant force of 15 newtons is applied to the wagon. So here comes that net external force. If it's applied to one of the objects in the system, then you could say it's on the system as well. The bottom picture displays the time in the future when the ball first reaches the other end of the wagon. Now, yes, there's rotation, there's rolling here. We haven't covered rolling, but that you don't have to worry about it for this question, okay? We'll talk about rolling with and without slipping after spring break. And so notice your center of mass of the ball is basically going to go from the front of the wagon to the back of the wagon. It's going to travel the length of the wagon, yes? And that's the timing that we're looking at. What is the acceleration of the center of mass of the ball wagon system? I'm going to pause for a second, see if y'all can figure this one out. Okay, so yeah, if you take a system approach, Newton's second law, F net on the system equals mass of the system times acceleration of the system. Let subscripts be your friend. And so we know the net external force on the system is 15. What's the mass of the system? 3. And then we're looking for the acceleration. No calculator needed. 5 meters per second squared. Good. Does the center of mass have a constant or changing acceleration? Justify, explain. So it's not, we know the number. Is it going to be a constant or changing acceleration? Why would it be constant? The force of yes. And so if we kind of look at Newton's second law again, well, the mass of the system, they don't mention any kind of change. So the mass is constant. And it says that the external force of 15 newtons, literally they said was constant. And so, whoopsies. Okay. So your acceleration has to be constant as well. Okay. C, rank the acceleration of the ball, wagon, the individual objects, compared to that of your center of mass. And so the wagon is going to accelerate what direction? To the right. And so just note to self, we know this was to the right. Your center of mass is going to accelerate to the It would be to the right. If the force is to the right, so your vector piece, your acceleration direction is determined by Newton's second law, by the direction of the net force. And so it would be to the right as well. And the ball, well, it moved from the front of the wagon to the back of the wagon. But if you look at the pictures, it's moved to the right. And so, yeah, inside the wagon, it's moving to the left, but from our outside frame of reference, from someone on the outside watching all this happen, it's to the right. So at least that part's good, right? Or correct? We know it's all to the right. Are they all the same though? No. So who's going to accelerate more or less individually? And we got to compare that to the center of mass. So I'm going to give an equation that it's the first time you're seeing it, but really it's not. Keep this in mind. Remember how we did mass weighted position? And then we changed the x's. Let me write it and then I'll talk. Okay. So we had mass weighted position as our center of mass equation. And then later we said, oh, well, your system, you can do the same thing for velocity. Well, guess what? You can do the same equation. It's a mass weighted average acceleration. Okay. And so we know something about the system center of mass acceleration. Now think about mass weighted average. Who's going to accelerate more? The timing is all the same, right? And so time equals 0, first picture. Time. Who's going to travel a greater distance in that same amount of time? Go back to the picture. The wagon covers a greater distance, so you can kind of look at the front of the wagon, x equals 0, to this side, x, w, f. Look at your ball, center of the ball to there. And your system would maybe be somewhere, you know, center of mass of your wagon, center of mass of the ball. And so this would be for your system. And so if you can kind of think about kinematics for the system and the objects, kinematics, we know the time is the same, the distances are different, the accelerations are going to be different. Who has a greater acceleration? And they all start at rest, so kind of in your mind be thinking about change in x equals VIT plus 1/2 AT squared. They all individually or as a system start at rest. Time is going to be the same for everybody. And so who has a greater acceleration? Acceleration is proportional to displacement. Hopefully that helps. Thinking about a mass weighted average. So who's going to accelerate the most? The wagon. Then who? Center of mass. And then the ball travels the least displacement up above. If you kind of look at initial, where does the ball start? Where does the ball end? And so we don't have grid lines up there, but using those distances as a gauge and kinematics, you can get your ranking. Good deal? All right. There are a couple other center of mass problems. I didn't do every single problem in the PowerPoint. So if you want to try some of those, you can. I want to end with a 2D collision mathematically. And so I think it's back on page, hold on. 6 was a problem that we skipped. And then there's an AP practice somewhere in that free response. So we can work on that one next time. So AP, they try to be clear about some things, but in the process, they're not always crystal clear. Bless you. Will you have to calculate, bless you, in full appreciation of calculation? Probably not for 2D collisions. Here's what they say. It's going to be a qualitative question, similar to what we already did, right? Or they say semi-quantitative. So you'll halfway calculate, partially calculate. What does that mean? So we're going to do this one, which I guess you could call it semi-quantitative. They don't give us math, so we're working with variables. Okay. It says billiard ball A is moving with a speed of 3 meters per second in the positive X direction. And so we see that. I'm going to go on and label that a positive velocity. It strikes an equal mass, yay, 1-to-1 ratio. Although we're not doing center mass on this one, okay? So just kind of dump center of mass for a second, go back to normal, collision. We have two objects that are going to collide. It's just now we're going to have some angles. So ball B is initially at rest. And so initial velocity of B is 0. And then they gave us 3 meters per second on A. Okay. Then the collision happens. The two balls are observed to move off at 45 degrees with the x-axis. And so this was not a head-on collision, by the way. This would be what's called like a glancing. And if you play billiards or pool, there's strategy to it. When do you want a head-on collision? When do you want a glancing? Well, if you're trying to get one of your balls to go into a corner pocket, but you're not lined up straight, maybe you need to hit that ball on the side and have a glancing collision. Okay. And ball B goes 45 degrees below. So 45, 45 is convenient. Notice they're 90 degrees separated after the collision. There's a simplification of math with that, but I'm not going to do that from the start because it's not always 45, 45. Okay. And it doesn't mean it's always 30, 60. I'm going to give you a setup. No matter what the angles are, it should work. What are the speeds of the two balls? So we've got two unknowns, yes? Say again. Right. Two different balls, they do have equal mass, and we have two unknowns. So VFA and then VFB after the collision. So first of all, there's a collision. So what's the gut instinct? What's plan A if you see a collision? Conservation of momentum, okay? And so since there's a collision, let's apply the conservation of momentum. Here's where it changes. Are you ready for this? I'm going to change color for impact. Momentum is conserved in the X direction independently from the Y. Why? Okay. So those two unknowns, I need two equations, and I think these are going to do it for us. Okay. And so take each one of them, and I'm just going to do horizontal first. So let's just think, where'd it go? There we are. Let's just think horizontally. So in the beginning, who has horizontal momentum? A. And so it's the initial momentum in the X direction of A. B starts at rest, and so no horizontal. In the end, who has horizontal momentum? Both A and B. So PFXA plus PFXB. Triple subscript. Each one serves a purpose. Okay, well, let's keep that one going. Maybe we don't need the other, right? So in the beginning, initial momentum for A is going to be MA V initial X. Well, thankfully, its velocity is all in the X direction. Equals, well, A has a horizontal, but now it's a final velocity. Plus MB and its final horizontal velocity. Equal mass. So MA equals MB. What can we do to simplify? Divide the whole thing by M. Equal mass. Gotta love it. And so then we can plug in the initial velocity of ball A before the collision, 3. But I don't know the velocities in the horizontal after. That's what we're trying to find. Well, is it? They didn't ask for the horizontal velocity. They asked for the speeds, what their actual motion was. And so let's think about a little triangle up above. Take a closer look at A. VA is at an angle. We have an X component and there's a Y component. You can't see the blue. This angle is going to be that 45 degrees. I know that I drew the triangle on the ball, but it would be whatever congruent. Think geometry terms, right? The 45 given with the horizontal is this 45 with the horizontal component. So my conservation statement includes the component VFX. How can I put it in terms of the hypotenuse? What trig function are we going to use? Cosine. And so I'm going to come down here and in place of VXB, I'm going to put VA. Technically, it's still a final. That's the hypotenuse times cosine 45 or theta, right? Let's keep theta for now. And it would be theta A technically. Maybe tomorrow they're not equal angle, right? Now we got to do the same thing, but for B ball. So if I go to my picture, it has a triangle with an X component and a Y component. Again, the 45 degrees is with the horizontal. Notice what trig function we'll use for the X component. It's still cosine. So they're both going to the right, so it should make sense. Now I'm putting different subscripts because again, tomorrow they may not both be 45. But here we are. Our two unknowns are the two hypotenuses, right? And so the next step, let's just simplify the cosine 45. Someone grab a calculator. And so make sure you're in degree mode always. And what would we plug in here? 0.707 plus VBF and 0.707. Everybody good there? And that's about as far as we can go here with this horizontal statement. So how do we solve for two unknowns? We need another equation. What's the other equation? Well, momentum is also conserved in the vertical. In the beginning, before the collision, who has vertical momentum? Nobody. 0. In the end, which ball has vertical momentum? Both. Notice now, one goes up, one goes down. We better take that into account, right? And so I'm going to go for the MV. Are y'all okay if I skip the P part? If we just go for MA, VFY plus, hold on, it did it again. Something I do, and I don't realize I'm doing it, makes a cursor thing. I can't write anymore. So I have to just switch out and switch back in. And that's a negative, actually. I'm going to make that a negative. You got to recognize that B goes down. And I don't think they told us down was negative vertical, but standard sign convention. Either way you do it, if they both add up to 0, can't I add the B momentum to the other side? So I can say MB V final Y equals MA V final Y. And again, MA equals MB, so what can we do? Cancel out mass. And the next thing, so this is the Y component of A is going to equal the Y component. And of course, it quit writing. Time out, hold on. Oh yeah, I need to reshare. It closes OneNote on me. Okay. Now you can see it. Now I'm going to try and write, cross my fingers. So mass is canceled. So VFY of A is going to equal VFY of B. Now those are the Y components. But where we left the other one off, those were in terms of the hypotenuse. So one more step, let's get the vertical statement in terms of the hypotenuse and theta. And so notice in both triangles, the Y components are the opposite legs, right? So we'll use what trig function? Sine. And so VA sine theta equals VB sine theta, and again, they may not be 45 each, so theta A, theta B would be a statement. Now I'm about to plug in 45. We're going to start seeing some nice simplification. But if it wasn't 45, you would just plug in, sine 40, sine, 37, whatever they are. And you could simplify, solve for one of them, and then plug it into the other equation, right? Similar to what we've done several times. But here, since they're both 45, do I even need to know what sine 45 is? Left side, right side, what's going to happen? It's going to cancel. And what they're basically leaving us with is that VA, which is a hypotenuse, is equal to VB, which is a hypotenuse. And we don't have a number there, but we have a concept. This is because of equal mass. It's because of 90 degrees. That's the trick, if you will. But now I can come in, and if both of these are the hypotenuses, and now I know they're equal, basically take the A and B off. So we get 3 equals VF times 0.707 plus VF times 0.707. Now it's just algebra. What happens next? You can pull it out, but if they're the same variable, combine like terms, right? 2. And so I get 2 VF times 0.707. And now you can breathe again, right? Now you can do the math simply. So calculate it out, divide both sides by 2, divide both sides by 0.707. What do we get for that final velocity? It doesn't matter really. And again, this is the hypotenuse. What do I hear? That's good. 2.12 meters per second would be for both. But be careful, this is unique to being equal mass and that 90-degree separation at the end. Don't start memorizing that all 2D collisions have the same speed at the end. That's not true, okay?
So what would be the next step to the sixth part of the equal?
If they didn't have equal angle, Okay, so over here on the green, if they don't have equal angle, let's say, so pretend, maybe it's 20 and 30 degrees. So I'd have VA sine 20 equals VB sine 30. Then just simplify, so solve for one of them. And then sine 30 divided by whatever sine 20 is. Sine 30 is 0.5. I don't know what sine 20 is, but it's bigger. You would just simplify the numbers that way. Okay? All right.